Okay, everybody, so 3:30, we are starting sharp. I'm very happy to introduce today's speaker, Erik van Sebille. He is a professor in oceanography and also in public engagement at the University of Utrecht. His background is in physical oceanography, also from the same university. And then he traveled the world for the postdoc with the University of Miami, close by, and also University of Sydney. And we discussed that we should not focus too much on the publications for evaluation, but if you Google him, you can see in the Google Scholar he has more than 100 articles on 10,000 sites. So he's going to talk today about some of the research that he's been doing in different areas, like quantifying the role of ocean currents in carrying heat or pollution, and also the impact of ocean plastic pollution and climate change on marine ecosystems. Thank you. Welcome.
Well, thank you, Omo, and thanks all for sticking around and for being here to hear this talk. So I always start with this figure just because it's nice and image, I guess, and you see all the colors, it's beautiful. It's my spaghetti plot, and it shows how ocean currents move stuff around. This is what I am investigating. So we're looking down on the North Pole here, if you don't see it, and each of those lines is a virtual particle that is moved by a simulation of the ocean flow. And our goal in physical oceanography is to understand this, to get patterns out of this. So essentially it's pattern recognition, but then really from the physics based. Now, this is a map where I've just colored all of the particles. You can also, of course, make an animation of it, looking now at the side, from the side of the globe. And this is if you start particles, virtual particles, everywhere on the surface of the ocean in a uniform grid, and just have the ocean flow carry those particles around. And then this is what happens. You see that very quickly the equator kind of empties out. The southern hemisphere also empties out, and here up the north. And all these particles accumulate in what we call the subtropical gyres. Two bands on the northern hemisphere and on the southern hemisphere where all of this stuff accumulates. And what I want to understand is why is it happening and how does the physics actually control the movement of plastic around? Not only on a large scale, but as I'll show in a few slides, very much also on a very small scale. And in particular, I'm interested in the interaction between very small scale physics and very large scale physics to create these accumulation bands, right? And if you have seen the news and have watched maybe some of the papers, and you know that this is this great Pacific garbage patch, right? The thing that Boyan Slat, my fellow Dutch countryman, wants to clean up. The one we can talk about that in the question time, maybe, what I think about that. But because I'm in a scientific computing department here, and this is the first time that I actually am in one, so I'm really excited. I wanted to show briefly about what actually the code is that we use to do this. What is it? What this simulation is showing, and that is about virtual, what we call Lagrangian particles. So virtual particles that do a Lagrangian analysis in an ocean model. And in essence, that is super simple. It's just a combination of interpolation and integration. So what you need to do is you need to have some kind of efficient I/O and some field caching, because we're talking about terabytes of hydrodynamic data on a regular grid that comes from the ocean models. That then needs to be interpolated to the point where the particle is. Those particles then need to be integrated through time. We may want to add and remove particles, so we need to have some notion of a dynamic list. And finally, we want to incorporate some kind of behavior, right? It's one thing to just affect virtual passive particles, but really the most interesting applications, including in biology, in plastics, are about particles that have behavior. Now, what we've been developing since 2017 is called parcels, which is a bit of a backronym. It stands for probably a really computationally efficient Lagrangian simulator. Yeah, we needed something for the P, right? But essentially, it's a set of Python class and methods for building Lagrangian particles. So it is a toolbox that you can use to then just build your own particle models. And we've used over the community has used in over 80 peer-reviewed articles, fully open source, of course, MIT license, you can do whatever you want with it. You can even sell it on a DVD, and I'm happy with it. And the key thing about ocean parcels is this behavior, right? How do you do this? Because anyone can create an interpolator and an integrator. That's 8 lines of Python code if you want. But how do you do this with this behavior? And then we think about, well, what kind of actions can particles actually take, right? They can move, advection by the passive flow. They can be diffused, some kind of random Brownian motion kind of walk. Maybe they can swim. They can actually hunt or reproduce, maybe if you think about fish, tuna. And even what we have now is particle-particle interaction on the short range at least. And that's of course an n-body problem, so it's not easy. But you do have it here and I show it. So this is a toy model where each blue particle is just a Brownian walker. The red particles are also Brownian walkers, but they have a region of influence. And as soon as the blue particles are within the region of influence, they get attracted towards the red particle. And that looks something like this. So what you see is that we now can have particles interact with each other. And say if this is if the red is a fish aggregating device and the blue are all fishes swimming around, then we can simulate here the interaction between tuna and their fisheries, for example, which is actually why we've been evaluating this. But the key thing is behavioral customization requires programmability. Right? If you really want to do this well, you need to code that up. And that's where parcels comes in. The way that we've been doing it is through kernel-driven computation. And a kernel is a way to encode an action, to put into a code some kind of equation. We've got pre-built kernels for advection or for diffusion, but the whole idea is that a user can encode anything that they want. Sinking, swimming, fragmentation, interaction, all of that, simply with a few lines of codes. Those kernels then get concatenated behind each other, and those kernels then get applied to the set of particles. So everything under the hood happens for the rest out of the concern of the scientist, the one who wants to build a particle model. And in that, we use the domain-specific languages paradigm, right? So this idea that there's a separation of concerns, right? That scientists like me, we are not meant to write good software. We're not trained for that. I don't have the time and the patience to actually write good software. I just want to solve my problem. And I'm sure that this is all familiar to you, but I just want to show here that I know this too, right? And I want to, and then I've converted to what you know. So anyway, and you've probably seen this all. Nobody can know everything from top level 7 science to low level performance optimization. That is why we have this domain specific language, and that's why how we build parcels. And I'm really, really proud of it because I think it is a really nice tool of software that we can work much, much further with. I mean, what's really cool also is that all these kernels get converted to C. So you write them in Python, but under the hood, they have a just-in-time compiler that then converts them to C so that they can run in C without the user having to think even about anything in that sense. So it's really accessible and easy to program. So give it a try, Ocean Parcel Store, if you're interested. And it's also a binder so that you can play around with it without having to install it. Back to the oceanography. So I said, right, that you have this accumulation of plastic. Plastic is not homogeneous in the ocean, gets carried with the currents. My question is why? Why does that happen? And in a big review paper that I led out of a SCORE working group, the Scientific Committee on Ocean Research, we came up with a list of, 12 types of processes, ocean processes that we think are important for the transport of plastic at the surface of the ocean, floating plastic at least, from large-scale open ocean processes to what we call submeso scales, so it's like on the kilometer scale or so, stoke drift, which is about waves, internal tides, the direct wind transport, wind roads and language circulation, vertical mixing, ice formation, river plumes, coastal currents, extreme events, and maybe even transport by biology. The challenge is that if you want to simulate all of these into one framework, then you need both a global scale and a very, very high resolution. And I'm not sure how often you've seen figures like these, but they're very common in climate science. Space, time diagrams, and the typical processes that we're interested in. And on the x-axis here is the length scale. What are the processes and what type of length scales do they have? And on the y-axis there's the time scale. Everything in green is covered by the numerical simulations, by what at CoAPS, what maybe you've heard of HiCom, that is all covered here, right? We can do the large scale circulation, geostrophic currents, boundary slope currents, eddies, up to kind of the submesoscale somewhere around a few kilometers or so, the tides, but only the residuals, so the net effect of the tides. Everything below there, everything yellow, we can't do just yet. My proposition is that we don't need to do this within a model. We can actually do this on the particles itself. So the particles, we know the physics, we know the equations that govern how the particles move. So why do we just interpolate the physics from the Eulerian grid on the particles if we can do it directly on the particles immediately? And this is a figure that came from a proposal that I submitted over summer. If this is funded, then I will have 5 years to kind of like come up with how to do this on the equations, on the particles, and come up with the equations that work for these. In principle, we have them. We just need to make sure that they work on a particle level rather than on a grid level. So, why would you want to do this? Why am I interested in how ocean currents move plastic around? I guess eventually it is because I want to know how the ocean works. I'll come back to that at the end. But also because, of course, I want to do something about this plastic, right? Like all of you, I'm worried. I see the pictures of plastic in the ocean, and I want to do something about it. And my proposition, my hypothesis, my working philosophy is actually getting more and more towards what do we do about the plastic? Well, there's a 6-point bullet list that comes to one conclusion. The first one is we need to realize that even though we talk a lot about microplastic in the ocean, and maybe you've heard about that, right? The microplastics that are in the animals. Sure, there are a lot of microplastics, and biologists worry about them because there are a lot of organisms that can ingest a tiny microplastic. There aren't that many organisms that can swallow an entire cobalt, right? So that is why microplastics have a large impact. But macroplastic is much more mass. Most of the mass is in plastic items larger than 5 centimeters. Something like 90% or more of all the mass of plastic in the ocean is larger than 5 centimeters. Most of the marine plastic originates from land. So it starts on land, and also it stays in the coastal zone for months to years. It doesn't immediately flush out to the open ocean, but it kind of like hangs around. And depending on exactly where you are, kind of bounces back between the surf zone, the beach, and the ocean, and the beach and the ocean, kind of like in this bouncing forth and back. And it can do that for years. The fragmentation to microplastics actually occurs on coastlines. It's on the coastlines where those large pieces, the entire bottles, the entire bags, where they fragment into smaller and smaller pieces. So that is actually, if you want to prevent microplastic, then you want to prevent that happening on coastlines. So I would say the cleanup on coastlines is actually very efficient. If you want to clean up the plastic somewhere, then do it on a coastline rather than in the open ocean, right? Because that's where it's come from, that's where it's still large. It's also much more energy efficient, of course. You don't need a big ship to go out there. And most important, well, not most important, but a nice bonus is actually that cleaning up coastlines is good for your mental health. There's this fantastic paper by environmental psychology, Kaylee Wiles, environmental psychologist. And she did an A/B test, essentially, where she sent people to the beach and assessed their mental health. And had one group just go for a beach walk, and the other group go for a beach walk and also clean up the plastic. And the people that cleaned up the plastic ended up with a better mental health. So if you are on the beach, and you do see a piece of plastic, it's actually good for you to pick it up. It's not only good for the environment, it's also good for you, right? So this is really, beach cleanups are the way to go. Now, of course, you're free to go to any beach that you want, and you can go anywhere but if you really want to do this at scale, if you want to scale this up, if you want to really put in a management solution to cleaning up beaches and thereby cleaning up the ocean, then you first want to know which beaches, which are the most important beaches then to clean up. And that is where machine learning comes in. I've talked to quite a few of you already, and everyone is talking here about machine learning. Well, we've been doing that too. And particularly, a PhD student in my group, Michael Kaandorp, he just wrote a paper on a machine learning approach to predict the beaching of plastic on the Dutch coastline. So this is the coastline of the Netherlands. And what we had was we worked together with an NGO, Stichting de Noordzee, and they've for 6 years been organizing cleanups on the beach, year after year after year, at every of those locations, roughly 10 kilometers apart from each other or so, where people have gone out, collected all the rubbish they found on the beach, weighed it so we know where that is. And because we have it for multiple years and for multiple points, we could actually test for, well, how can we create a model that predicts where this plastic ends up? And because I'm among friends here, I thought, well, let's get the full dirty laundry out. We were reasonably able to do that. I'm quite actually curious to know whether you think that this is a good model scale. I mean, it's published now anyway, but I don't care anymore. But this is what we ended up with, right? So here's the observed value, and here's the predicted value. The black line is one line. The red line is actually the variogram. So that's the internal variability essentially of the data itself. 95% of the data I need fall within that variogram, so we can't really do much better. But what we do get is a slight under prediction of the extremes. So our model doesn't predict as high values for the highest and as low values for the lowest values. But we get R's of 0.7 or so for 5 tests. It's okay. I think at least it got published. But the key thing here is that we were able, because we used a random forest approach, we were able to actually find out which of the predictors that we put in, which of those are the most, the most skilled, or the most important in terms of their Gini importance coefficient. And here you see for the top 10 of them, what their Gini importance coefficient was. And the coloring here is that everything that's blue has to do something with the tides. We knew when the data was collected, when the cleanup was performed. So we know what the tidal phase was. And you see that those are by far the most important. The red ones all have to do something with the currents and the flow itself. And interestingly, the yellow ones have to do something with the sources of plastic, where the plastic comes from in the first place. And those are not nearly as important as I would have expected. And I think the reason is that there's just enough plastic floating around in the North Sea, right? There's this kind of like reservoir of plastic, and whether it ends up on the beach really depends on the tides and the currents, but not so much on whether there's plastic coming from a river at a certain point. Or so can I just continue, or is this a technical question? Or like okay.
The currents, where do you come from?
CMEMS, I think. Yeah, with tides, including the tides. Yeah. So we are kind of able to predict where plastic comes from. But if you remember the title of my presentation, it was about the blame game. Can we also say whose plastic it is that we find on the beach? And that's where Bayesian inference comes in, right? So that is essentially a Bayesian question, because if you essentially it comes down to asking the question, if I find plastic at a certain beach, location X, what's the probability that it came from a certain source S to start with, right? And this is framed immediately, you see, as a Bayesian question, which you can then rephrase as the probability of the plastic at point X coming from S is the probability that if the plastic that comes from a certain source ends up at the location X, times probability that came from a certain source to begin with, divided by the probability that it is at that location to begin with. Now, this one is the likelihood, and we can calculate it with our simulations. That is what they do, right? We start particles somewhere at a certain source, and we track them forward in time. So this is literally what ocean parcels is meant to do. PS is the prior, and that says something about, well, what do we know about sources of plastic to begin with? And there are many data sets of how this can be done in the ocean. And then the most difficult one is actually PX, because essentially it is the probability that there's plastic at a certain location. And that means that you can only calculate this if you know the whereabouts of all the plastic in the entire ocean. Or if you know from all the sources of all the plastic everywhere in the ocean. That is an open problem, and we're not there yet. What we have been doing so far is that we converted to the closed problem, where we just take into account that it is plastic that comes from any of a finite set of S. So we define a certain set of S, how many sources we look, and then we look at what's the probability that the plastic found at point X is from any of the sources S. So then this essentially becomes a normalizing term, right? So it becomes really simple. But we had a lot of trouble thinking this through and thinking, okay, what do we do with this? And now I understand why most people in Bayes inference actually drop this altogether. It's really annoying. But maybe it's good to show it here that why it is so. So we did that. Actually, Bram van Duinen, a undergraduate student who worked with me for a few months to play around with this, he came up with how to do this in backward time. And the idea is essentially that you start particles somewhere, you run them through the simulation, through the flow field, and that gives you a probability that the particles are somewhere after some time, right? And then you overlay that with the probability of the sources at the same time. And the convolution of those, that's essentially the likelihood that it can, or sorry, now I shouldn't say like, this is the likelihood, and this is the posterior, essentially, right? That's the way to think about it. And he could do this for a certain one of the beaches that was measured in the Netherlands. Maybe, I don't know how good your topography knowledge of Northwestern Europe is, but here's Netherlands, here's Belgium, by the way, the UK and France. And he was able, from this yellow cross here, to calculate backward in time, what is the probability if you find a piece of plastic at a certain date over here, that it came from any of the coastlines in red, any of the rivers as these circles, or any of the known fisheries grounds, where we knew that there are data sets of where fishing is happening at any time in the ocean. How that is related. And you see that well. So most of the time it came from somewhere here on the east coast of the UK, but sometimes also almost from the North Sea and everything, right? So you can really now, if you find a piece of plastic, start to point, okay, this is where it came from. Except that there's still one really big unknown, and that's shown over here. This is namely the single parameter that we have left. The age of the particle. How long has the particle been in the water? Because of course it matters. If you find a piece of plastic on a beach somewhere, whether it's been in the water for a few months or whether it's been in the water for a few years, of course the sources are going to be different. And you see that here too. So here we see from that same location and in that beach in the Netherlands, we see what the probability is that it came from any of the sources from age 0 to age 2 years. With all of the hashed is the fisheries, and all of the non-hashed is from rivers and coastlines. And we see that, well, for the very young plastic, it's all orange, so that's Dutch, so that's the local plastic, that makes sense. But the older the plastic gets, the longer it's been in the water, of course, the more it gets blue in this case, which has to do with the east coast of the UK, in this case. And this is a parameter that a model can't tell us. We need to find this, we need independent data about how old a piece of plastic is, if we ever wanted to say something about its origin. So we're working with chemists to think about, well, can we say something about state of degradation, chemical degradation, oxidation of the plastic, to say something. But we're also working, for example, with archaeologists. So with a team of archaeologists in the Galapagos Islands, who are, if you think about it, an archaeologist, what they do is they they take an item, an artifact, they call that, and they reconstruct a story, based on what they see. That is what an archaeologist do. And you can also do that for pieces of plastic that you find in a scientifically valid method. I mean, what archaeologists would call scientifically valid. To really very carefully analyze, well, what is it that we found? And a really nice, I think I have time for that. A great story about this is from when we were doing this in Svalbard Island. So Svalbard Island is up in the Arctic, near in the north of Norway. And we, a group of, I wasn't there, but my collaborators cleaned up all the beaches of this island archipelago. And they collected the plastic that they found and they categorized it. And they categorized it into, for example, cosmetics. So those were shaving creams, deodorant sticks, shampoo bottles, all the things that had to do something with cosmetics. And then they very carefully looked at, okay, what do we see? And there was an archaeologist there who said, that's strange. They're all male products. So on this island of Svalbard, all of the cosmetic, or almost all of the cosmetic products found on the beaches were men's shampoo and men's deodorant. That's not because they drift another way, right? It's not left shoe, right shoe. That's a fake story. It's because we think it's because of the sources. They are from the fisheries, from the local fisheries, from the fleets fishing around in the Arctic in Svalbard. And that really clearly points to that as being a source. Because if it would be a source somewhere on land, if it would be a landfill or so, you would expect much more homogeneous between male and female products. So that is really what archaeologists can tell us about the origin of these items. Another thing which is also really exciting is biology. By carefully looking at the growth of organisms that grow on plastics, the barnacles, the algae, the biofilm that forms on anything that's put in the ocean, you can kind of like get a handle on where it could have come from. And say something about that. And Ian Suthers and his group in Sydney have been doing quite a lot of work.
So a quick question. In your model right now, each piece of plastic is independent of every other piece?
Yes, so far it is. Yes. Yeah. The density of plastic in the ocean is sufficiently low that they won't interact with each other. Yeah. No, good clarification. So assume that we know where the plastic is on the beach, and assume that we know whose plastic it is so that we can know who to send the bill to. And the next question is, how do we most efficiently clean it up? Right? What is the most efficient cleanup strategy in terms of where to go, when to go, so that you can do that? And it's one thing to think about that for the Dutch coastline. It's actually much more interesting to think about this in the Galapagos. And this is a big project that I've been involved in for a few years now, where we want to make the Galapagos the first plastic-free ecosystem in the world again. Right? In other words, if you can't do it in the Galapagos, then we have no hope of doing it anywhere else. Right? Because the Galapagos is iconic, it has low population density, it's very well controlled by legally controlled. And if you remember from my very first animation, the currents move away. It was in the zone that very quickly emptied out because there's upwelling, because the water comes mostly from the deep. So we're trying to do this in the Galapagos. And one of the things that in the Galapagos, only 3 of the islands are inhabited. Most of the islands that you see on this map are uninhabited. And there's really only one city over here. So the park rangers who we work with, they want to know when and where to go out so that they can actually clean up their plastic. And that is also where we use scientific computing, because we want to, Stephanie Ipma, a postdoc in my team, created a network analysis of the connectivity of all the beaches and all the coastlines around the different islands, and how floating plastic would move from one beach to the other. It looks something like this. So this is the connectivity graph based on the different islands of how plastic would move from a certain island to another island. You see that most of the time it goes from beach, it's local, it goes from one beach to the next, it's within the island at least, but there's also some significant cross-island movement sometimes. And now what she did, and this has just been published 4 weeks ago or so, is that she then used network tools to find the optimal locations of intervention. So essentially to look at betweenness, the source sink information. So network characterizations of where, if you want to go to one place, then what's the most effective place to clean up the plastic? Right? It may not be the most polluted beach, because if the flux of plastic going to the beach is very low, if it's just been accumulating for a very long time, sure, you clean it up once, but yeah, you don't really get a lot of plastic out of the system. It may be much more efficient to go to a beach. There's a very high in and out flux. And if you go multiple times, then that is the efficient place to actually take out the plastic. And that's what we're trying to do with those metrics. I'm only showing 4 here. In total, you try 10. And super annoyingly, and if anyone has an idea, they all show something completely different. So the managers that we work with don't like this. Actually, got a lot of pushback on this, saying, what are you telling us? Where do we need to go now? And we said, yeah, well, I mean, depends a bit on what it depends, he said. Slightly annoying. We need to solve that in some way. So if any one of you has some ideas, I'm still around tomorrow. I'd really love to talk about that, but how to do this better and how to really more robustly think about which is the most important of all the metrics. Because we want to take this further, right? So this is just the beginning, right? We want to really develop an app for the park rangers that uses all of this and the data to predict where, as I said, the plastic will wash ashore. And then we want to do this for the Galapagos, but also for other archipelagos, right? It would be great if you can export this to other systems in Indonesia and in Svalbard, as I said, in Greece, who don't know, and then clean up the beaches and help people predict, okay, when and where is it most effective to go to the beach. So that is in half an hour, the oceanography. But as Olma already mentioned, I am not a professor of oceanography. I'm a professor of oceanography and public engagement. And I want to spend the last 10 minutes or so to talk a little bit about that, about what this public engagement part is. I mean, it all starts with the idea that we are in a climate crisis, and solutions to the climate crisis rely on at least some form of climate literacy among the public. Right? I mean, that's not the only, that will not solve it all. It's not the sufficient condition, but it is certainly a necessary condition. And the ocean plays a key role in climate, right? Through storing heat, storing carbon, moving plastic around. So the ocean is certainly an important part of the climate. But I think that if you want to talk about climate, then there are a few reasons why it's actually really good to talk about the ocean, or to use the ocean as an entry point into climate. And one is that the ocean is enigmatic. It's exciting, right? We know more of Mars than of the surface or the bottom of our own ocean. It's fantastic to be, well, so here we were recording a children's TV show in the Netherlands on the beach with talking about the overturning circulation and the Magellan circulation, all that. It's always nice to talk about the ocean. People immediately have emotion. I've never met someone who's indifferent to the ocean, right? The ocean is also important as a link for sustainability, because thinking about plastic, for example, it links socioeconomic choices to perceived remote impacts. What do I mean with that? We all here in this room, I'm sure that you've stood in a coffee bar and thought, I'm not going to take another takeout cup, or I'm glad that I took my reused cup because I care about the ocean plastic, right? Or I'm not taking a straw today, or I'm not taking a recycling bag because I care about the turtles in the ocean. And it's kind of bizarre if you think about it, right? That what we do right here in Tallahassee or anywhere in this country, the chances of that plastic actually ending up in the ocean are very, very low, unfortunately. Right? But still, people make the connection. They make the emotional connection between what we do in our economy and the impact that it has on turtles and marine life. Even if that's not really very clear, so they perceive at least that there's a choice. So it connects daily lives with and daily life choices with the environmental impact. And the other thing is that the ocean is a commons, so it's a shared responsibility. So we can use it to talk about an international perspective, and it doesn't immediately get into national interest and fighting between continents and countries. It is really ours to do. So that is why I think it's interesting to think about public engagement, science communication from the point of the ocean. But more in general, I think it's interesting to think about science communication, right? I mean, it's really bizarre if you think about it, right? All parts of the scientific workflow have a protocol. We know how to set up a study, we know how to write proposals, we know how to peer review, publish, test hypotheses, set up simulations, all of that we have a protocol for until we start to communicate about our findings. Then we do it on intuition, right? And I'm not sure how many of you here have been in media and talk about it. We often do it just, because it feels. So my research question here is, how can academics actually be most effective in their public engagement, in their science communication? And it includes things like, well, what is the actually added value of scientists in the public debate? When should scientists speak up, and when is it better if professionals do the science communication? Right? Does it actually help if it is a professor on television or a scientist, or if it's a weather broadcaster, for example, on television talking about climate? Which roles, persona should scientists take, right? I mean, should we be the honest brokers, or should we be the pure scientists? But also more in a narrative form. Should we be talking or acting as warners? Or should we be acting as saviors? Should we be the heroes of the story? Or should we maybe even be the villains? Right? What helps? What is the best way to communicate our science? And how should we as scientists put ourselves up there? And also related then to that is, how do you actually define the limits of expertise? We all talk about science from our own expertise, but where does it actually end? Right? I mean, I once got a call from a colleague who was really annoyed because I was talking on the national broadcaster website about something about the overturn interpretation in the Gulf Stream. And that colleague said, no, that's my topic. Why do you talk about it? Right? So I think there's a lot of envy and a lot of frustration between scientists, among scientists, and care. And actually, if I'm on television, and I'm quite frequently in the Netherlands, I'm not worried what my mother will think about it. I'm worried what my colleagues will think about it. And that's really bizarre if you think about it. Because shouldn't we all be here with the same goal of raising literacy, scientific literacy? I mean, why are we constantly pushing ourselves down, each other down? That is really something that I want to understand. And most interestingly, activism, right? Is it okay for scientists to be activistic? There's one part of it is the moral implications of this, right? Should we be activistic? But even if you let that go, I think another important question is it effective for climate scientists to be activists? Or does it hurt our trust if we are seen as being too activistic? And an interesting study here, so I'm now on a sabbatical. I'm on a 3-month sabbatical. That's also why I'm here in Tallahassee this week. Really to read up on all this literature, because coming from this as a physical oceanographer, there's a lot of learning that I have to do about science communication, literature, communication science, public engagement. Reading 2-3 papers a day on this topic to really get up to speed with what's happening. And one of the most interesting reads that I've had so far, in the 5 weeks so far, is from a paper out of Canada a few years ago with Ed Maybach, who's a quite famous name. Maybe some of you have heard of him. He's in George Mason University. I met him when I was in DC. We had a beer. I said, I finally meet someone who I've read a paper from. I felt like a graduate student again. Kind of funny. But what they did was they did an analysis of credibility of a climate scientist. So what they did was they created a persona, a fake climate scientist, who would then write stories, who would make statements. And then they had a survey, a national survey, Colloquium survey or so, and have people read those statements and then reflect on the credibility of that scientist. And the thing is, so that credibility was on a scale from 1 to 7. And the thing is that if the scientist talked about recent findings, then the credibility was 5. And this is in the US, right? So this is good news. I hear a lot of people saying, but no one trusts scientists anyway. That is not true. Credibility is very, very high, even here in the US still, for climate scientists. If that person then started to talk about the risks and the impacts that his finding had on daily livelihoods, that credibility didn't actually change. He was still as credible, even in the US. If he started to talk about the policy options and the consequences, right? I mean, what can we do about it? And what policy options are there? And what does it mean for daily livelihoods? That credibility, it didn't drop. If he really talks about, well, we need to take action right now, not specific, but really there needs to be some action, credibility still high. Even if he talks about CO2 reduction, the credibility was still relatively high. It didn't drop that much. It was only when he started to talk about nuclear power as a solution that the credibility actually drops. That's interesting, right? So think what you think about nuclear power, but as climate scientists, don't talk about it. That's kind of the rule. But the point is that people trust scientists, and people also expect, and that's another study that I read, the public expects us to be warners. And because we are taxpayer funded, if we realize something, if we find something in our data, we should speak out about that, because that is the expectation that is happening. So that's to wrap it up. I will start with this, taking it back to plastic again. Yes, sorry it became 2 presentations, but that is, I mean, I have a split personality now. That's what it is. But the main point, I think, from the plastic is that, of course, the plastic that's littering in our oceans is an atrocity, right? Society, we all should be ashamed that there's now plastic on the deepest parts of the ocean, under the sea ice, found everywhere. But at the same time, it's also an opportunity to better understand how the ocean works, right? So trying to use this to train our models, to improve our models, do machine learning, all these kind of things. So use the silver lining. And then the 3 take-home messages. So small-scale processes that have a crucial role in the transport of plastic. Challenges to capture these processes in numerical simulation. Accurate numerical models could be used to optimize beach cleanup strategies and play the blame game through Bayesian inference. And then I talked about the ocean and how it provides a unique opportunity for scientists to engage with the public. And the question that I want to answer is, well, how do we actually do that most effectively? So before I wrap up, I really want to give credit to all of the team who's done this, right? I haven't done this alone. I've done hardly any of it. Most of the work has been done by the fantastic PhD students, postdocs, master students, bachelor students, anyone who's worked with me over the last 5 years in my team. Those are the true heroes of the story. I'm just a warner or the villain. Thank you.